ultimately, so now we're recording. Ultimately, you know, in chapter 6, we want to see some applications of what we're learning here. Okay, this chapter 6, which is the section on hold on here. It's a section on orthogonality, and least squares. We ultimately want to see an application of all this. So that's going to come up next in section 6.6. But before we get there, we have to talk about least squares problems, which is section 6.5. So let me give you a moment to copy this example down. Okay. Okay. So here we have a matrix. We have a matrix A that has 3 rows and 2 columns. And we have this vector B that's a 3 by 1. So the system of equations AX equals B, well, that system, the matrix A, of course, is as I said, it's a 3 by 2. Vector B is a 3 by 1. So what's going to be the rows and columns for the vector X? The vector X would be a what? Something by something. It has to be a something by something. How many rows? How many columns? Good. That's right, Eleanor. 2. That's a 2 by 1. So you have here a matrix equation which represents a system of equations. How many variables are there? How many variables are in our system of equations? Well, the vector X is a 2 by 1. So how many variables do we have? And I understand your hesitation. This is kind of, you know, you're thinking about this. But if the vector X is a 2 by 1 vector, how many variables are there? Well, let's see. Vector X, hold that thought. There'd have to be 2. That's right, Catherine, and I appreciate all responses. The vector x is a 2 by 1 vector. So there has to be an x1 and an x2. Has to be an x1 and an x2. So, okay, well, so I have two unknowns, and let me turn off that email. I don't want any distractions here. Hold on here. Hold on, everybody. One moment. Okay. So we always think of equations. We have a certain number of equations, certain number of unknowns. Blank number of equations in blank unknowns. Well, we have two unknowns in this for our system of equations corresponding to a times x equals b. How many equations do we have? How many equations are going to be in this system? Well, I'll tell you what. Let's go ahead and we'll write it out a little bit, and this will help us. So we want to see if this system has a solution. Okay, in other words, is the system consistent? So let's go to the next page. And we're going to try to solve a times x equals b. And you can see here that, a times x, if I use the row column rule for multiplying the matrix A times the vector x, then I'm going to get this system of equations. So we have three equations and two unknowns. And sometimes when we have that, it's referred to as an overspecified system. When there are more variables than unknowns, it's sometimes referred to as an overspecified system. How many maybe have heard of that? An overspecified system of equations. Okay, Benjamin has. All right. And it doesn't mean that the system doesn't have a solution, but if it were to have a solution, there would have to be some redundancy in the equations, right? There'd have to be some equations that are for an overspecified system. There'd have to be, I want to be careful how I phrase this. There'd have to be some equations that are equivalent to each other. All right, but that being said, let's see if our system has a solution. So, of course, what I'm going to do is I'm going to set up the augmented matrix here. And I'm going to do some row operations. And that gets me down to here. So let me give you a moment to catch up. Please so as you know, with we never want to forget our row operations because that helps us just stay connected to the theory behind linear algebra. I mean, row operations are important. So of course this number 4 here, well, I decided I want to just multiply the first row by a fourth. So then I have a 1 as a pivot. And then I want to produce 0 in this last row here. And so I'm going to multiply the first row by -1 and add it to the third row and put the result in the third row. Okay, and then, all right, so let me just give you a moment to catch up here. Okay. So now we get down to here, and I'm going to use this one here as a pivot to produce a 0 in the row below in the column. And we always keep in mind that this is an augmented matrix. May I move to the next page? Are there any questions? All right. Well, so what I want to do now is I want to take -1 times the second row and add it to the third row and put the result in the third row. So let me just write that down. I took -1 times the second row and added that to the third row. And put the result in the third row. Okay, that's what I did. And remember, it's an augmented matrix. So the last column here, or the last row, presents a problem, right? Because that row stands for this equation. 0x1 plus 0x2 equals 21/2. Well, that has no solution. So that means that this system of equations is inconsistent and has no solution. It has no solution. Okay. Give you a moment to catch up here. Okay, so, mathematically, we can see that this system of equations has no solution. And that happens. That happens a lot, right? That happens a lot in applications. So, well, if we can't get an exact solution to a system of equations, we can find what's called a least squares solution. We'll get to that. To understand a least squares solution, I want us to look geometrically at what's going on with our system of equations here. And so we started out with the matrix equation, A times X equals B, and that represented a system of 3 equations and 2 unknowns. Okay. But the 3 equations were all different, and we found there was no solution. But what does A times X equals B mean? Well, the system A times X equals B, that matrix equation can be written as this vector equation. X1 times column vector A1 plus X2 times column vector A2 equals B. So the matrix A consists of column vectors given by A1 and A2. And those column vectors, A1 and A2, well, A1 is equal to the vector 4, 0, 1. That's the first column of the matrix A. The second column of the matrix A is equal to 0, 2, 1. So geometrically, what we're doing when we try to solve the system A times X equals B, geometrically what we're doing here is we are trying to see if there is a linear combination of the column vectors A1 and A2 that will equal the vector 2, 0, 11. Okay, 2, 0, 11, as you recall, that's the B vector, right? All right. Okay, now we know that a linear combination, in other words, x1 and x2 values, do not exist because there is no solution to this vector equation, which is equivalent to the matrix equation. Okay, so we're tying a lot of things together here. Okay. So in a way, I'll restate what I had just stated here. May I move to the next page? Are there any? I want to make sure I'm pacing myself well. All right. All right. Okay, so what we're doing is we are looking, in this process, what did we do? We are looking for x1 and x2 such that this vector equation holds. Okay, which I'm basically restating what I just stated. And I'll make a little note here that the column vectors A1 and A2 are not orthogonal. Okay, but we were looking for x1 and x2 such that this vector equation is true. And we can think of the span of the column vectors of the matrix A, which are A1 and A2. We can call that subspace W. The dimension of subspace W equals 2, and W is a subset of R cubed space, three-dimensional space. But since x1 and x2 don't exist, we couldn't solve the system. This is geometrically what we have here. In terms of a picture, this is geometrically what we have. In terms, so a geometrical description of the system of equations is here. Let me give you a moment to copy this down. We'll talk a little more. Okay, so let's now again, we were trying to solve the system. We were trying to solve our system A times X equals B. And that system of equations as a vector equation was equal to X times column vector A1 plus X times column vector A2 equals the vector B. Well, this vector equation here had no solution. So that means there's no linear combination of vectors A1 and A2 that would equal the vector B. So the vectors A1 and A2 lie in subspace W, but the vector B has to lie outside subspace W. It has to lie outside the column space of the matrix A. The matrix A, of course, the column vectors of the matrix A are the vectors A1 and A2. So since the vector B cannot be written as a linear combination of the column vectors A1 and A2, that means the vector B cannot be in the subspace. It can't be in that subspace W. It has to lie outside of, the vector B has to lie outside of W. And this is what we mean geometrically when a system of equations cannot be solved. This is the geometric interpretation of that. Okay. Are there any questions? Are there any questions? Let me ask you a question. Let me ask you a question. If the, hold on here, yeah. If the vector B were a linear combination of A1 and A2, where would the vector B be drawn in the picture? Can somebody maybe draw that vector B in the picture? if the system of equations did have a solution, okay, that means the vector B would be in the subspace W. So where could we draw the vector B? Where should it be drawn if that were the case? Can somebody maybe put that in the picture? I mean, I can do it, but I just was curious if anybody wanted to volunteer. So if the system of equations had a solution, then the vector B would be a linear combination of vectors A1 and A2. So the vector B would be in subspace W. Okay, and therefore, in that case, you would draw vector B here, right? That's where vector B would be. But we don't have that situation. Are there any questions on that? Okay, well, all right. All right, so I wanna take this sort of a nice easy approach here. So if, I mean, we agree that x1 times a1 plus x2 times a2, okay, for any values of x1 and x2, where would those vectors lie? Where do these vectors here, any vector that's a linear combination of column vectors a1 and a2, where would those vectors have to lie? Where would they have to be? Where would they be drawn relative to the picture? What space would they be in? In other words, okay, let me think of it like this. So I'm glad I'm doing this. This is, okay, you're thinking here. So x times a1 plus x times a2 is in what? That's right, Benjamin. Good. It's in subspace W, because subspace W is the column space of the matrix A. And the column space of the matrix A means that's the span of the column vectors of the matrix A. And the column vectors of the matrix A are x1 and x2. Okay, so I'm going to draw here a few vectors in my column space of A. I'm going to draw a few vectors in there, okay? So, well, hold on. I need the line here. Okay, there's a vector. I'm going to draw maybe three vectors here, okay? Okay, I'm going to draw three vectors. Whoops. Okay, and I'm going to label, hold on here, let me get my little, whoops. It's very picky, very picky. Okay, I'm gonna call, like, I got vector 1 here, vector 2 here, and vector 3 here. Okay, and I don't know why that showed. Just forget that line there. Which vector do you kind of like the best, class? Vector 1, 2, or 3? Which do you kind of like the best? Of those vectors that are in the subspace W, which one sort of stands out to you? Vector 1, 2, or 3? Okay, I'm getting different answers here. Getting different answers. Let me try this again. Hold on. I'll do this quick. I don't know why these lines, they just kind of pop out of nowhere. I don't know why. Getting some different answers here. Okay. And I don't know if this approach is going to work. I'm trying to sort of give you an appreciation for something. Let's put it that way. That's what I mean, really. Ah, come on. Right angle there. Okay, so vectors 1, 2, and 3 are all drawn in that subspace W, which is the column space of the matrix A. And all of those vectors 1, 2, and 3, are some linear combination of the vectors A1 and A2, right? Because any linear combination of the column vectors A1 and A2 is in the column space of the matrix A. So which vector, put it this way, which vector, instead of saying which vectors do you kind of like, which vector kind of is special of those 3 vectors? Which vector is vectors 1, 2, and 3, which is kind of the special vector? Okay. So I'm curious, Eleanor thinks 1. Abby thinks 3. And I welcome all thoughts here. Well, do we have a few more responses? Eleni thinks 1. let me ask you this, and I appreciate all responses. Abby, you had said that 3 was, you feel, a special vector. Why? Why do you think the vector 3, and that's really the vector I was going after, the vector 3 has a special quality to it? What's true about the vector 3 relative to the vector b? Maybe I should have said that. Relative to the vector b, okay, which of the vectors 1, 2, or 3 seems to be special? I think then you'd all say vector 3. Why? What makes vector 3 special relative to the vector b compared to the any other vector? Okay, Haley, that's right. It is the vector 3 is the projection of the vector b onto subspace W. It is, because we have here this right angle here. And also that means then that the vector 3 is the closest vector in subspace W to the vector b that's outside of W. The vector 3 is the closest. So the projection of the vector b onto subspace W is a special vector, and you know, there exists some linear combination, some x1 and x2, okay, some scalars x1 and x2, such that we will get this projection vector 3, okay? And those scalars, those special values of x1, are called x1 hat and x2 hat. And the vector x hat, see, I'm putting a hat above it, the vector x hat, which would consist of x1 hat and x2 hat, is what's called the least squares solution. The least squares solution. All of these vectors here, all of these vectors, like the vector 1 here, is equal to A times some vector x1. The vector 2 is equal to A times some vector x2. Okay, the x2 vector would be, you know, some vector with values x1 and x2. But the vector x3 is the vector that is equal to A times x sub hat. And that's the vector 3, that is the closest vector in subspace W to the vector B. Okay, are there any questions on that? All right, give me a moment here. Okay, let me bring up the ebook here. One moment. So this is what I was getting for trying to convey to you about this section. The vector b in figure 1 here, the vector b is closer to a times this vector x hat than to any other vector a times x for any other vector x. Right? And in fact, all right, in fact, the idea here is that, let me see, let me just, yeah. The idea here is that if a times x hat, if the difference between that vector and the vector b, if that distance is smaller than the distance between the vector b and any other vector a times x, we call the vector x hat a least squares solution of our system of equations. I mean, if we can't solve the system of equations exactly, if we cannot get an exact solution for the vector x, the best we can do is get the least squares solution. Because think about it, if a times x, well, okay, think about it like this. Oh, I love this. So this is good. Hold on. If a times x equals b, if that has a solution, and I'm saying suppose here, suppose a times x equals b has a solution. Well, what does that imply? And when I say has a solution x. What does that imply then about the difference between ax minus b? What would that equal? That equals the zero vector. That's right, Haley. Okay. But on the other hand, let's suppose that ax equals b has no solution. Okay, let's suppose that ax equals b has no solution. What does that imply about the difference between the vector ax and b? What does that imply? That good, Benjamin. That means it's not zero. Okay. So for the first case, all right, the first case, if AX equals B has a solution, then when we take the difference between AX and B, those vectors, that's just equal to the norm, or the length of the zero vector, and that equals 0, right? This is the perfect situation. But for this case here, when AX equals B has no solution, that means that the length of AX minus B is what? Is what? It is well, not equal to 0, but also, that's right, but can we be even a little more, can we say anything else? That's right, greater than 0. That's right. Okay, so what we want to do is, okay, well, the ideal situation is when we have a solution. And when we have a solution vector x, the difference between the vector a times x and the vector b is 0. Well, okay, if we don't have a solution, then we know the difference between the vector ax and the vector b is greater than 0. So since 0 is ideal, what we want to do is we want to find a vector x that minimizes the distance between the vectors ax and b. So the best we can do in this case, for this scenario here, is find a vector x. I'll call it x hat, such that the difference between ax hat and b the difference is less than or equal to the difference between ax minus b for all other values of x. For all other values of x. And this vector x hat is called our least squares solution. So do you see, and why is it called a least squares solution? Well, if you think about when you find the distance between two vectors, the distance is the sum of a bunch of squared terms. Now we take the square root of that, but inside the square root we have a sum of a bunch of squared terms. We want to minimize the sum of those squares, and that's why we call that the least squares solution, the vector x hat. The question is now, how do we find the vector x hat? We know the vector x hat. Well, are there any questions on that? Okay. Well, then let me go back to the book if we're good on this. All right. So if I go back to the book here, this now makes sense. This makes sense. Okay. In other words, when a solution to a system of equations is demanded and none exists, the best one can do is find a vector x that makes a times x as close as possible to b. And that vector x is your least squares solution. Now the question is, how do we find it? How do we find this least squares solution? Okay, how do we find it? Well, all right. Of course, we have to recognize, okay, that, and this is figure 2 in the book, that the a times x hat, which equals b hat, not b, because a time, we can't, no value of x would be such that a times x equals b, because we don't have a solution to our system of equations. But a times x hat would equal b hat, and b hat is the projection of the vector b onto the column space of A, which we all, I think, are comfortable with. The vector b hat, that projection vector, is the closest vector in the column space of A in that subspace to the vector b, which is outside the subspace. So how do we find the this x hat? Well, okay, we can take advantage of a few things. For instance, the projection vector b, I mean, you can see it even in the picture. The projection vector b is orthogonal to the difference between the b and the b hat vector. That's like the z vector that you're used to seeing. So b minus b hat is, no, scratch that. That's incorrect what I said. No. Look at the vector b, look at the vector b hat. B minus b hat is that vertical vector, okay? It's like the z vector, so it's like that dashed vertical vector that you see there in the picture in figure 2. Well, b minus b hat is the same as b minus a times x hat. Okay, that's the same thing. And b minus a times x hat is going to be orthogonal to each column of the matrix A, because the column vectors of the matrix A are in that subspace, the column space of A in figure 2. So b minus ax hat, and they show that vector there in the picture. That's orthogonal to any b minus ax hat is orthogonal to any column vector of the matrix A. And so that means that the dot products of every column vector of the matrix A, okay, with the vector b minus ax hat would have to equal 0. Or equivalently, the transpose of the jth column vector of the matrix A times the vector b minus ax hat, that would have to equal 0. Okay, are there any questions on that? It's absolutely beautiful stuff, absolutely beautiful. Okay, so for every column vector of the matrix A, AJ transpose times B minus AX hat equals 0. Well, collectively speaking, since the matrix A consists of the column vectors, we could take the matrix A, transpose it with B minus AX hat, and get the 0 vector, right? And so this is the key then to finding what X hat is, because matrix multiplication is distributive. So equation 2 could be written as, if we distribute the A transpose on the left side, okay, if we just, hold on, did I lose the book here? Hold on, no, sorry, let me, shoot, hold on. I hope I didn't lose it long here, hold on, let me see. Okay, good. So, how long was the book out, class? Just for a second, right? Did I get, like, what I'm trying to say is just for a second. Okay, all right. So again, thank you, Benjamin. A transpose times B minus AX hat equals a 0 vector. Okay. By virtue of the fact that every column vector of the matrix A is orthogonal to the vector B minus AX hat. And the matrix A consists of all the column vectors of A. A transpose times, if we distribute A transpose on the left there to the B and the AX hat in equation 2, then we will get A transpose B minus A transpose A times X hat equals 0. And that means then that A transpose times AX hat would equal A transpose times B. And so the least squares solution has to satisfy this system of equations given by A transpose A times X equals A transpose times the vector B. And this system of equations, they call these the normal equations. The normal equations. And a solution of 3 is denoted by X hat. So the set of least, this then proves theorem 13. Hold on. Yeah, this proves theorem 13 then, that the set of least squares solutions of AX equals B coincides with the set of solutions to those normal equations. Okay, are there any questions on that? So now we know how to find the least squares solutions. Now we know how to find those. Okay, how many think this is a pretty cool proof? How many find the geometry helpful for understanding what we're doing? Okay, lots of, okay, thank you, Eleanor. Thank you, Catherine. All right. Well, now let's go back to the problem we were looking at, and let's see if we can find the least square solution to that system of equations. So we're going back here. Okay. Back to the Future, right? So anybody seen that movie? I don't know. I was just a teenager when that came out, but I don't know if you've heard of that movie. Okay, Catherine's seen it. All right. It's a good movie. It really is. Natalie has seen it too. All right, great. Incidentally, I think Back to the Future, I think they're making a sequel. Now, Michael J. Fox, as you know, he has Parkinson's disease, but he's lived with it a long time. And I think they're making a sequel. I don't know if you've heard about this with Doc Brown and Michael J. Fox. I don't know, but has anybody else heard that rumor? Or all right, well, okay, all right. I agree. I agree, Catherine, definitely. All right, let me give you a moment to copy this example down. Okay, so again, here we are. The matrix A, the vector B, the same as we had in the earlier example we looked at today. And since the system AX equals B does not have a solution X, what we want to do is we want to find the least squares solution X hat of the system AX equals B. And then we'll determine the least squares error for the least squares solution. Okay. All right. Are there any questions before? May I go to the next page? Maybe give me a thumbs up if you're ready. All right. Christopher, you're good? All right. Okay, so we're ready to go to the next page. We're good? Maybe. All right, excellent, excellent. Thank you, Eleni. Thank you, Abby. All right, so just to refresh ourselves here, what we're doing, okay, here's another picture of the situation. We have the vectors A1 and A2, the vector B hat, that's outside the outside the subspace W, which is the column space of the matrix A, and the vector B hat is the projection of the vector B onto the column space of A. B hat is the closest vector in subspace W to the vector B, and we know that there is a solution, and I really should call it a least squares solution, right? There is a least squares solution such that x1 hat times a1 vector plus x2 hat times the a2 vector equals the vector b. And further, we note that the difference between the vector b and the projection vector b hat is smaller. It's smaller than any other the difference between the vector b and a times x hat, which is the projection vector b hat, that difference is smaller than the difference between the vector b and any other a times x vector for all x and r squared. Okay, so that's a little bit of review there, but nevertheless. Okay, let me know if you have any questions. And I'll note here too that for that matrix A, the column vectors 4, 0, 1 and 0, 2, 1, those vectors are linearly independent. So in this example, the column vectors of the matrix A are linearly independent. And now we're going after the least squares solution. So naturally what we have to do is we have to set up the normal equations. Okay. All right, and we'll do that. All right, so give me a thumbs up when you're ready to go to the next page. Okay, very good. All right, here we go then. Okay, so this is our the normal equations come from this matrix equation. A transpose times A times X hat equals A transpose times B. So it's really computational. A transpose times A, well, that's remember, A was a 3 by 2, and A transpose is therefore a 2 by 3. So A transpose A is a 2 by 2. Okay. And A transpose A will always be a square matrix. Wait, scratch that. Yes, that's right. That's right. That's right. Um, Now A transpose B equals 19 and 11, that vector. And I'm going to find the inverse of A transpose A. Okay, and I'm going to show you why I do that. But um, I'm going to find the inverse of A transpose A. And remember, earlier on in the semester for a 2 by 2 matrix, you had a special formula for the inverse of a 2 by 2 matrix. That was back in, let me see, that came, one moment, I should know the section. That was back in section 2.2. 2.2. Okay, so that's from section 2.2. So what do we got? We got 1 over A D minus B C times a matrix that has, D, negative B, negative C, and A. How many recall that formula? It's been a while, but okay. Good, Benjamin. Now, there's a comment below that A transpose A is invertible, but sometimes A transpose A is not invertible. And in that situation, well, they have example 2 in the textbook that shows you what to do in that situation. Basically, in that situation, you'll solve a system of equations and row operations will be involved. But we're trying to get the normal equations, solving them would involve row operations. But in our case here, we're going to try to take advantage that A transpose A is invertible. And it's invertible, incidentally, because the column vectors of the matrix A are linearly independent. Okay. And in the homework, you're actually going to prove that result as one of the multiple choice questions. I think you are. I think you are. All right. Or maybe, well, yeah, we'll see. We'll see. Okay. Are there any questions? Are we ready to move to the next page? Just give me a thumbs up when we're ready to go. Okay. All right. So Let's proceed on then. Okay, so here are the normal equations that we want to solve. And it turns out okay, normal equations, right? We can multiply through this matrix equation on the left side by A transpose times A inverse. And when we do that, we'll get then that the least squares solution x hat is equal to the inverse of A transpose times A transpose times B. And when you work through the computations, you'll get it that the vector x hat is equal to 1, 2. That's your least squares solution. And of course, A times x hat will equal the vector b hat, right? It'll equal the vector b hat. Which is the projection of the vector b onto subspace W. Now, normally projection vectors, right? In the past, you've had formulas to compute projection vectors, right? But those formulas, like the formula that you learned from the orthogonal decomposition theorem in section 6.3, that formula depends on the fact that that formula works to get the projection vector only if your basis for your subspace is on an orthogonal basis. Well, our vectors, A1 and A2 for the column space of A, which was our subspace, those vectors are not orthogonal. So we can't use section 6.3 to get the projection vector b hat. We can't, we have to do it this way. Are there any questions so far? All right. Well, if you're good with that, then let's finish up the problem. So the problem was, well, we found the least squares solution, and now we want to determine the least squares error for the least squares solution. So I'm going to have to compute, hold on here, I'm going to have to compute A times x hat. Okay, and so the least squares error is found as follows. I compute A times x hat, okay, which is going to give me 443. And then I will subtract the vector 443 from the vector b. And that gets me -2, -4, and 8. The least squares error would then just be the difference between that vector b and a times x hat, or the vector b hat. And you'll see next week that line of best fit through data points, which is sometimes called a least squares line or a regression line. That kind of problem can be expressed as a linear algebra problem. Are there any questions? All right. All right. Well, so what we showed here then, I'll go ahead into the book then, if you're good. May I move to the textbook? All right. Thank you, Abby. Okay. So what was demonstrated here? What was demonstrated here is this theorem from section 6.5. Okay, this theorem, theorem 14, and in this theorem, all these statements are logically equivalent. Okay. If hold on, let me get this. Yeah, if you have a unique least square solution, that means the columns of A are linearly independent. And A transpose A is invertible, and then you have the formula. And you've actually, but what happens if you have a matrix A where the columns are not linearly independent? Okay. Well, that relates to the second example. So let me go up here. Whoops. Second example, they want you to find a least squares solution of AX equals B for this matrix A and this vector B. Why is the why are the columns of the matrix A linearly dependent? Why is that true? The columns of the matrix A are linearly dependent. Why is that? That's right, Benjamin. Column 1 is the sum of the other three columns. If you add columns 2, 3, and 4, that will equal column 1. In other words, column 1 is a linear combination. Well, column 1 is equal to 1 times column 2 plus 1 times column 3 plus 1 times column 4. Okay. So let's go ahead and get the normal equations for this. Here you go. Now here A transpose A. Okay, they compute it out. They compute it out, and you know you have a 4x4 matrix here, and that matrix, that square matrix, is not invertible. Why is that? How do we know that A transpose A is not invertible? The matrix that's, so the first column 6, 2, 2, 2, and then you have the other three columns. That matrix, that 4x4 matrix, is not invertible. How do I know? How do we know? Well, what can you tell me about the columns of that square matrix, A transpose A? That's right, Catherine. The columns are not linearly independent. As a matter of fact, the first column is equal to the sum of columns 2, 3, and 4. In other words, the first column is a linear combination of columns 2, 3, and 4. So, you know, we can't use a formula that involves A transpose A inverse. So what we have to do is we have to work it out. Okay, we have an we figure out A transpose A, we figure out A transpose B, and then you have an augmented matrix here. And after doing some row operations, you get that matrix in reduced row echelon form. And it turns out that basically we kind of have what I might call chaos, a little bit of chaos, because is the least, we have some free variables here. X4 is free, and you solve for X1, X2, and X3. Okay, and you get your least squares solution here. And is the least squares solution unique? Is that least squares solution unique? For example, 2 is x hat. X hat equals what? 3, -5, the vector 3, -5, -2, 0, plus x4 times -1, 1, 1, 1. Not unique. Because why is that, Benjamin? Why is that least squares solution not unique? X4 is free. So it's kind of like chaos. That's how I think of it, because I'm used to my projection vector being the single most closest vector to the, I mean, if I have a projection of a vector B onto a subspace, I'm thinking that projection vector is the closest vector in the subspace to the vector B. But in this case, and then hence there's one least squares solution x hat, but that's not the case here. So this really is just kind of a little bit of chaos going on there. That's how I think about it. We have multiple, I guess. We have multiple least squares solutions and multiple vectors that are equally close to the vector B. Multiple vectors that, infinite number of vectors, since x4 is free, you can have an infinite number of x hats, least squares solution vectors, and that would give you an infinite number of vectors that are let's say this the right way, that are in the column space of A and equally close to the vector B. Okay, wow, Okay, I'm not sure that's too desirable, right? But at any rate, there it is. You can see how important linear independence is for the columns of a matrix. Uh, okay, are there any questions before I stop here? Okay, I'll stop the recording.